Okay, it's just after 2 p.m. Eastern time, so I think ready to get started. Um, Thanks everyone. First of all, thanks everyone for joining us. It's great to see such great numbers showing interest in sensitivity analysis and missing data analysis. So today I'll be talking about sensitivity analysis with a particular slant in this webinar on clinical trials and pharmaceutical industry. My name, by the way, is Andrew Grannell, and I'm the Senior Statistician here at Statistical Solutions. So what am I going to cover today? I'm going to walk through what is sensitivity analysis, why should you do sensitivity analysis. We'll do a bit of a couple of examples in SOLAS there to give you a good overview of how to handle it in a practical approach, and then we'll also cover some questions and comments that you may have. And just for the format of this webinar, feel free at any time to put a question to me. Just pop it through the text box there that is provided by the GoToMeeting window. And at any stage, if you think the webinar window is too small, you can enlarge that by using the zoom function at the top left-hand corner of the GoToMeeting webinar screen. Okay, so just a bit of background information first. In recent times, the FDA, the Food and Drug Administration, asked the National Academy of Science and Statistics to investigate missing data analysis and the appropriate way to approach missing data analysis. A committee was set up, and this working group created a report called the Prevention and Treatment of Missing Data in Clinical Trials. And in this, they had several recommendations on how to, first of all, prevent missing data, all the steps you can take before you even start the clinical trial, how you can prevent it, including follow-up procedures and all that. And then how, when you do get missing data, because everybody recognizes that you do get missing data and it's very easy to get missing data, that how do you deal with that, appropriate ways to approach missing data, and then how to analyze the data once you've dealt with missing data. And a few facts here. It's estimated that greater than $7 billion is spent every year on the evaluation of drugs, devices, and biologics. And also it's been highlighted that randomized clinical trials are the primary tool for evaluating new medical interventions. Randomization provides a very fair comparison between treatment and control groups no matter what you're looking at. But it's always important to ensure that randomization takes place. So when missingness starts popping up and starts occurring, this can have the effect of reducing the benefits of randomization and introducing this thing of bias into your data and bias into your analysis and bias into your inferences and into your results. So this committee wrote up some extensive guidelines on how to design and conduct clinical trials and analyze the data, because there's very limited advice out there on handling missing data. Currently and up until now, there's been many approaches tended to be ad hoc, and there was people presenting different approaches that they took. But at the moment now, we're into this new time frame where you can set up a dialogue with the FDA, and they're willing to engage with how you're approaching your missing data analysis, and you can set up a conversation there. So there are modern tools out there that reduce this potential bias, and this panel that was set up encouraged these approaches. Multi-imputation is a method that cropped up that they really feel strongly about, and they felt that this is a strong method to use to approach missing data analysis. And then what goes hand in hand with missing data analysis is this thing called sensitivity analysis. And this is probably the most important step at the end of your missing data analysis. And it is important in the sense that it assesses the degree to which the effects rely on the assumptions. So when you're doing your missing data analysis, you have certain assumptions, you make certain assumptions, and this sensitivity analysis assesses the validity and the correctness of the approach. So, as I just said, sensitivity analysis we feel is the most important part of the missing data analysis because it really adds this verification and validity to the results that you're presenting. It's a relatively new topic, and it's been brought up on us because of these constantly evolving new methods out there. The literature is always changing and always popping up new methods and new approaches, and a lot of that is due to the massive increase in the computation power and the memory in computers, so the strength of the computers. The theory is relatively young as well. It dates back to the 60s and the 70s, but the computation power now exists that we can really take advantage of this. We can really use these methods where now the computers aren't slowing down. They can actually handle this vast amount of computing time and effort and power. So sensitivity analysis is essentially the stress test of your assumptions. So you're making several assumptions, or whatever assumptions you are making when you're doing your missing data analysis, such as your distribution assumptions, is it normal, not normal, outliers, influential observations, can we call it an outlier if we don't have an appropriate representation of the overall population? So these things are questions that are asked. What are the assumptions about the missing data? Is it missing at random, missing completely at random, or not missing at random at all? And then also information that may be in or not in the data at all. So you may need to bring in informative priors. Non-informative priors are additional or auxiliary data. So let's just take an example here that's given at the beginning of Dan Rubin's book. Say this is the overall population. We know that this is a distribution of an overall population for a specific variable with a mean mu, and it's obviously normally distributed here. Now we do a study or a survey on this population, and we take a sample, but it turns out that the guys who respond, they all fall into one half of the distribution. So now, after conducting our study, the respondents that fell into the left-hand side of the normal distribution, we know nothing now about the guys in the other side. So, how do you approach this? Now the data looks skewed, so you have to use the appropriate analysis methods for this. But what the actual population looks like is a normal distribution. So what appropriate measure do you use? Do you use means, medians, or do you take the lowest value? And in this case, if you took the lowest value, that would be closer to the actual population mean of this parameter. So if you use complete case analysis, the data looks skewed from that point of view, and you're going to be using certain methods that would actually be not appropriate for investigating the overall population. So, and also, what about if outliers pop up? If this guy looks like an outlier because it's outside our collected data, and this is one of the people that was in the left-hand side of the normal distribution, it looks like it's an outlier because it's not close to any of the data that we've collected, say that's in this part of the distribution, but yet it's actually quite close to the population mean, but we don't know that. So all these things pop up when you're dealing with missing data, and it all comes around by trying to make an accurate inference about the population that you're doing the study on or doing your trial on. Okay, so how do we define? So these are the questions you have to ask yourself. How do we define outliers when it's a missing data case? How do we know that an outlier is not the true mean? And there's ways to do this using model-based methods, such as predictive model-based, which is a linear regression-based model, predictive mean matching, which is a logistic regression-based model, and this combination method that we have in SOLAS, that is a combination of 3 different models. So what we offer in SOLAS is 2 different methods of modeling the missing data in relation to the data that you've observed. And what imputation is based on the information you have and that you've collected in your trial. you then can fill in the missing data using an educated or accurate guess as to what that answer should be based on the information that you've already collected. So in SOLAS we offer 5 methods of multi-imputation, and they cover 2 main approaches, a matching approach and a model-based approach. The models are mainly regression-based, so you've got this level of non-linearity. Obviously, regression models perform best when linearity is high. If there's an overlap between the outcome variable and the covariates, in the model-based method, it can be used as a predictor, and then the correlation between the two in a model-based, correlation doesn't affect too much. When you're looking at matching, you're looking at finding the most appropriate observed case to use to impute into a missing case. So you use some characteristics that are similar between 2 cases, and you take the observed one and you impute it into the missing one. So these matching methods are handy because it's insensitive. It's not sensitive at all to nonlinearity. That doesn't apply. There does need to be overlap between the outcome variable and the covariates, and it performs best when the correlation is high. So let's look at sensitivity analysis in SOLAS then. So what you would do in SOLAS is you'd take your incomplete data set, you'd run your analysis just to get your complete case analysis as a comparison, as a starting point. You then create several imputed data sets for each imputation method. Now you can go off and check your assumptions first, or you can just run the methods. It's quite easy, and I'll show you in a minute. It's quite easy to run these methods anyway, so it's not a labor-intensive approach, because SOLAS is engineered so that it's quite easy to run these imputations, and it's quite easy to run analysis after you do your imputation. Then we need to investigate the methods, the approaches, and how they're performing based on the results of any subsequent post-imputation analysis. And then we need to make an informed decision on which method is best to use for the actual analysis and reporting purposes. So let's turn to SOLAS now and do a quick worked example. And again, if you have any questions, please don't hesitate to put them in through the text box there, and we'll get back to you as soon as we can. And I'll take some time as well to answer some questions at the end. So at any point, just put in the question. There'll be a record there when the question comes in. So at any point, if you have a question, just type away. Okay, so I'll open up SOLAS there now. So here's what the SOLAS window looks like. And if you need to zoom in, again, the zoom function is at the top left-hand corner of the GoToMeeting webinar window. So here we have options to open a new data set, create a new data set, or open an existing data set. And as you'll see, it looks quite similar to a spreadsheet Excel file format. There's also a script language option, so that you can write your own code to create your own imputations, or you can generate an imputation using the interface here, and SOLAS will then generate the code, and you can alter little bits of the code, so you don't have to write out everything from scratch. You can do a specific imputation and then change things to your liking afterwards. And also there's quite extensive help functions and manuals to help you along the way. So I'm going to use quite an easy data set here just for example purposes. It's called treatment miss, and it's a data set with 9 variables and 188 cases, and these are patients, and we have some specific personal information about them, like their age, their height, and their weight. We have this treatment variable here, which is a categorical variable, which tells us whether they were treated or not. And then we have various readings. We have their cholesterol value, that's a recording, and we have measurements for dose 1, 2, and 3 for 3 separate drugs. So the 3 characteristic variables, age, height, and weight, they're all complete variables, and so is treatment. And then these 4 variables here, cholesterol, dose 1, 2, and 3, these are all incomplete variables with missing data points because these were all measurement based. So that tends to be a common source for missing data these days. So so firstly, what you might want to do is just get an overview, is just examine the missing data pattern. What does it look like? How much missing data is there? What does it look like? What variables are popping up that might have a lot of missing data in them? So this is the interface again for selection windows. So it's literally quite easy. You just drag and drop. So you pick up one variable they want to use, and you can drop it into the variables to display box. But what I'm going to do is we can use the use all box here, so I'll use all the variables just to get a quick overview. So what we have here is we have this kind of cell formed table where the blue cells represent a missing data point and the white cells represent observed data point. And then we also have a box here for the list of the variables that we have. So again, there's 188 cases, so it's not a big data set exactly here. So if you were to scroll down, it's not too bad, but if you had quite a large data set, it would take you quite long to scroll down. So we also have this collapse feature. So now we're able to collapse down the data set. So what this is telling me now is that there are 141 completely observed cases out of the 188. There are 2 specific cases with this specific missing data point. There are 42 with this specific missing data point. So this might be something that you might want to look into for actual follow-up, say. And it tells you here in the display this it's the cholesterol variable, and there's 42 missing cases. So you might want to actually, before you do your analysis, do a follow-up on the cholesterol value, see if you can, recover any of those readings or anything. So that's the missing data pattern window. It's quite a handy feature, and again, you can copy and paste this quite easily into a Word document for reporting purposes. Okay, so now I'm just going to do quite a simple, very easy, just a simple t-test between 2 groups to see if there's a difference between 2 groups. So I just go Analyze and T or non-parametric test. And now we have the window again, which is just a drag and drop window where we have the option of doing a 2-group t-test, we have a pair group or 1-group test. So I'm going to compare the treatment groups for cholesterol value to see if the cholesterol values are the same between the 2 treatment groups, yes or no. So I want to see if the treatment group has a higher or lower cholesterol value than the guys who weren't treated. So I've dropped the treatment variable into the grouping variable box and cholesterol into the outcome variable box. And click OK. And now up pops my output window. So here what I have is various descriptive statistics like the mean, standard deviation, and a 95% confidence interval. And then at the bottom here I have my t-test statistics. Also it runs, there's an option you can run the equivalent non-parametric test if you feel that the data is not normal or non-parametric. So as you can see here, there's 146 here cases for cholesterol to be used, and 73 in the treatment group. So 73 per group. So yes group, the guys who were treated have an average cholesterol of 243, and the no have an average of 222.8. So that's a mean difference of 21. And we can see here that the t-test is telling us there is a significant difference between the 2 groups, a p-value of less than 0.05. And we also have the Levine's test for equal variance. So, so that's just to bear in mind before we do any missing value or missing data analysis. the complete case analysis is telling us that there is a significant difference between the two groups. Now I'm going to run an imputation. Actually, I'll just show you a scatter plot here as well between cholesterol and age. And I can actually group that by treatment group. So now here's the scatter plot for the two groups. We have a couple in the yes treated group. We have a couple of data points here that might need further investigation, but we'll bear that in mind for later on. So now what we'll do is we'll do a couple of imputations here. So a predictive model based, this is the linear regression model based method. And simply what you do here again is you just click and drop. So I'm going to use these characteristics, the patient characteristics like age, height, and weight. I'm going to use these as the fixed covariates. So these will help me define the imputation. So I want to take people with similar age, similar height, and similar weight. I want to take these people and find the corresponding people for the missing values and impute their observed values. So that's how I'm going to set up the donor pools. So you can also select how many imputations you want to do. I'm just going to do 5 here for an example. So 5 imputations, and SOLAS you can do a maximum of 50, so you can create 50 data sets. I'm just going to create 5. Click OK, and up pops a new spreadsheet window, but this time they are complete data set. So, and here we have the data filled in, and if you look down the bottom we have 5 tabs, 1 for each data set. So this is quite a handy feature. 5 data sets that I just created, and these are 5 complete data sets. Now I'm going to just show you the exact same scatter plot, cholesterol versus age. I'm going to split it by treatment group. So now we have the same scatter plot here. On the left hand side is the no group, and on the right hand side is the yes group. And now we can see something a little different here. There's some red triangles now and there. And what these red dots are the actual imputed values. But it's the imputed values for data set 1, because that's the data set I was on when I plotted this graph. So this is only for data set 1. I now can actually overlay the other 4 data sets to show all 5 imputations on the one plot by simply going View, Multi-Imputation, Show All Plots. And now it's going to overlay all 5 on each and show a line just giving the spread of each imputation. Now I'm actually going to modify the x-axis there on that one. Now, so now you can see all of them. So there is one value there, and obviously that got re-imputed to someone else who was similar. So this may not be a complete outlier, whereas this one may be. So as you can see here, the imputations quite closely follow the spread of the observed data as well. So this is a nice handy feature, and again these can be copy and pasted into any Word document or whatever for reporting purposes. Okay, so now I'm just going to move on and do that t-test, the exact same t-test that I did before, but now I'm going to do it on the complete data. So I'm going to use cholesterol as the outcome variable and treatment as the grouping variable, and I'm going to test if there is a difference of no means. So here's our output window again, and now we can see our descriptive statistics. Now for the yes group it's gone up to 240, and for the no group it's gone down to 226, giving us a difference of 13.7, and that's for data set 1. So again, data set 2, 3, 4, and 5. So there's output for 5 data sets, all given on the same window, which again is a very handy feature. And then we have this combined one here, and I'll come back to this in a second, but as you can see here, this gives us the mean value for each across all 5 data sets. So the mean yes, the mean no, and the mean difference for across all 5 data sets. So quite a handy feature. Now, that was one of the model-based methods. So that was is this down? So that was one of the model-based methods. Now I'm going to do one of the matching-based methods. So I'm going to use propensity score matching and see if there's any difference there. So again, I'm going to set up the imputation the exact same way as I did before. Use the 3 characteristics to set up the matching, and I'm going to impute the 4 missing or incomplete variables. I'm going to do 5 imputations, click OK, and now it pops my 5 data sets again in the same window. And now I'll do a plot again, scatter plot, this time using the matching method, one variable. Click OK, and then I'm going to overlay the other 4 data sets, and now you can see quite a difference here and here with the yes and no groups. So with the model-based method, it didn't pick up a match for this data point, but it did for this data point. And now with the matching-based method, it did the opposite. So immediately you can see a difference in the approach taken by each method. And now I'm just going to run that exact same t-test again. Cholesterol broken down by treatment group. Click OK. And now is for data set 1. We can see that, wow, previously it was, for the original one it was 11. Now the difference for the model-based was 13, and now the difference here has jumped up to 22. And you can see then that this is corresponded to a significant difference. And that's across all 5 data sets, except for that one. So this is interesting. So now we've got we've used 2 different methods, and we've 2 contradicting results. So now what do you do here? And this is where a lot of people have a lot of problems. So I'll just go back to my slideshow now. And I'm aware of the time there, so I'll just get through this. So here is if you did all 5 methods, here's a summary of the results. And you can see here for the top 3 here, these are the kind of the model-based methods. You can see that the difference between the 2 groups is 11.5, 11.7, 11.6. And these all correspond to a not significant result, not significant different result. And then if you do the 2 matching methods, propensity score and Mahalanobis distance, you get a result, a much higher difference between the 2 groups, and you get a result that is significant. Now what you would do here is you would now have to examine the underlying assumptions for both approaches. And I'll go back up to that slide, this one. So as you can see here, the data was linear, but it'll turn out that there wasn't a good overlap, and the correlation was not that high. So that's what happens in this case. So you can see that the underlying assumptions for the matching methods fell down, whereas the linear models or the regression model based approach worked out quite well. So and that's the same slide showing you the significant difference. So just to summarize here, because I'm aware of time and I'm aware you're all busy, it is important to tackle missing data when it arises. Missing data analysis can reduce potential bias in your data and in your analysis and results, and then the sensitivity analysis gives a validation to your missing data approach. So as I said before, if you went off and used the matching methods because it gave you a different answer to the original data, the complete case analysis, you also have to be able to stand over the assumptions that are made for the matching method. Here, the assumptions for the matching methods didn't hold valid, so that wouldn't be a valid approach, whereas the model-based methods, those assumptions made did hold up, and they are safe to use in your analysis. Now, the next step is to perform your analysis on all those data sets, all the imputed data sets and compare the results, and they should be quite similar. So these recommendations were made to the FDA by this this committee, the panel that I told you about earlier, who the NAS panel who wrote the report on the treatment and prevention of missing data in clinical trials, and they feel strongly that multi-imputation is quite a valid approach to missing data analysis, and they also feel very strongly that sensitivity analysis should go hand in hand with multi-imputation. So I'd like to thank you all for attending this webinar. I hope you found it very useful and interesting. I'll take some questions now, and if you don't have any questions right now, but you might have some later on, we're also going to be putting up a recording of this webinar on the website, and we'll be sending out these slides to you. So if something pops up later on, feel free to email me at my email, andrew.grannell@statsol.ie. My LinkedIn page is here if you want to communicate with me that way, or my Twitter page is there. So I'll just take a minute there to look at a few questions if any questions have come in, and then we can